out. And the thing coming from the sun that we protect ourselves from, with regard to wearing sunscreen, of course, is UV, ultraviolet radiation from the sun. So we talked that there's UVA, UVB, and UVC. They're listed in the way I did them in order of increasing energy. So UVC is the worst. But most of UVC, like we talked about on Friday, actually is removed in the stratosphere. So UVA and UVB gets through, and this slide actually kind of talks about, as you probably already know, we need some sunlight. We need to expose our skin to some sunlight because it's a good source of creating vitamin D for our bodies. And then this says, actually, can you think of something else that's good for your health? Like ultraviolet radiation is good for our health, but too much of it is a bad thing.
I actually watched a video last night for my anatomy class, and it was like that the sunlight is actually better for us because the vitamin D that we're getting is producing nitric oxide on our skin, and then that helps the blood.
Instead of taking like in a pill form or something like that?
Yes.
Mm-hmm. Yeah.
And they said it's like 100 times more likely to die from a heart disease than it is from skin.
Ah, interesting. And D and the nitrous oxide and everything, it helps heart health?
Yeah, it helps like thin the blood vessels and raise the blood pressure.
Yeah, I don't know. There's so many things in life. You're like, do I fly? Do I drive? You know, it's like, do I expose myself to the sun? You know.
So many more people died when they were playing in Russia.
Speaking of, how many?
71.
I didn't hear that yet.
Flight.
So I don't know. So what do you think? Are there other things that some is good, but too much is bad? Food, actually, yeah. We need food to live, but too much food, and yeah, we become unhealthy. Anything else? I was gonna say maybe wine. Wine actually has some good things to it. Too much wine's probably not good. Alcohol?
Kind of like one glass a day.
Yeah. Beer here and there.
So there's a shot.
See, you know,
I'm good.
one glass a day of wine. Yeah. So some alcohol here and there, but too much is not good.
She doesn't take a blood thinner.
She uses that.
Yeah.
The thins her blood.
The doctor said it's fine.
So it's during the summer, sometimes if you're like me, you kind of look at, before you go outside, the weather forecast will give you a UV index for the day. And that UV index, it looks like I hit a word here. The word is sunburn, risk of sunburn. So the UV index is an indication of the intensity of the rays basically at that time. And as you might imagine, it's a function of many things, including, looks like I have a word here, ozone. We're going to talk more about ozone. We talked about pollution ozone in the troposphere, but as some of you guys know, in the layer above the troposphere, the stratosphere, there's good ozone layer that actually helps us to block some of the radiation coming from the sun. So what's the ozone like in the stratosphere? What sort of elevation are you at? And what sort of cloud cover do you have? So those three main factors go into giving you an index number for the day. So, you know, and I don't know enough about the creation of vitamin D and how our skin actually welcomes the ultraviolet to create the, so I'm not sure how that works, but kind of keep that in mind. The higher the number, then you're more likely to, in a short period of time, go ahead and burn. All right, so on to part 3. Dun, dun, dun. So with all this chemistry, I'm gonna have to try to focus that. It just looks a little fuzzy to me. But of all this focus on the pollution in the atmosphere, but also here in a minute we're going to talk about that protective layer in the atmosphere. Need to remember what this looks like. Of course, we have the troposphere down here. Now, the green bars mark the locations of the kind of the barrier between the troposphere and the stratosphere. So we have this whole thing's the stratosphere, okay, and the ozone layer. I used to think it's up here in the stratosphere, but the ozone layer is kind of in the lower part of the stratosphere. I have a few things. If you've ever, and I don't know, I haven't flown much. I've lived a sheltered life, but what this is describing is that if you are, I think what it's trying to say is if you're up at higher elevations, okay, so your plane is cruising up here. Wait, oh, I guess not the mesosphere. Your plane is cruising up here. I do think it bumps up against the, I think planes kind of go in the stratosphere because they like the nice, okay, so your plane's up here. Now, one of the things before we talk about these two things, what about the thickness of the air? Is the air thicker or thinner up here?
There's a thing, there's jet airplanes on the side.
Oh, jet airplanes, thank you. I do think they can, okay, jet airplanes. I'll double check, but I think some of them. But so you're flying up here, the air is thicker or thinner? Thinner, yeah. And so all this is saying is that with that thin air, that your pilot has to work harder to get it to slow down because there's fewer gas particles. Now here's one for you. Oh, looks like the word fewer. Here's one for you. If you are cooking something using boiling something, sometimes it will say at upper elevations you need to boil it for a longer period of time. And the reason, again, you go up now. The highest mountain, Mount Everest, actually doesn't extend from the troposphere and the stratosphere. But if you go up in the troposphere, air thins, and actually water will boil at a lower temperature. Water boils at 212 Fahrenheit, 100 degrees Celsius, usually, down here. If you climb a mountain, the air's thinner, and it's going to actually boil at a lower temperature. So that's why they say go ahead and boil it for a longer period of time. So the word I hid was there's less air pressure at higher altitudes. The trick, though, have you ever heard a trick to go ahead and how can you, well, I'll just put it in the form of a statement. You actually add a dash of salt to your water. It's called boiling point elevation, and salt to your water will make it boil at a higher temperature. So actually, if you're a higher elevation, consider adding a little bit of salt, and then it's going to boil at 212 Fahrenheit instead of that 200 Fahrenheit or whatever it is. Okay, so those both have to do with the atmosphere being thinner, and you guys already told me that people get out of breath as they struggle to breathe as we climb mountains, and that has to do with less oxygen. Okay, so I'm just curious. Anybody in here just kind of throwing things out? Have you ever heard about the ozone layer, or what comes to when you think of the ozone layer? Is there anything in particular you think about, or what?
The hole in the ozone.
The hole in the ozone layer. We're going to talk about that.
I feel like I've heard it in a science class.
Right? In some science class, how that works. Ozone layer. Okay. Well, on the previous slide, or the previous, at what elevation is the ozone layer located?
Stratosphere?
It's in the stratosphere. Does on the sides there, the kind of the left and right, I think it gives elevation. Is there an elevation?
15.
Okay. Very good. And just to see that we're all on the same page, what is the formula for ozone? It is O3, yep. Which molecules make up the ozone layer? So the ozone layer is going to be O3, okay. Do you think the ozone, oh goodness, sorry, O3, there's my O3. So do you think that there's nitrogen and oxygen? Yeah, it's just, think of it as just thinner nitrogen, oxygen, still basically an 80-20 mixture with O3 molecules up there. So this is kind of not necessarily drawn to scale, although maybe it is. And the green bars here now indicate the ozone layer. So of course we have the troposphere next to the Earth. So what's this little, the way this works is as along the x-axis we have increasing ozone concentration. So why is there's this little tail here? What's this ozone right here?
Man-made stuff.
It's man-made stuff. It's the pollution. That's the sad face. You pull the sad face. Okay, and this is our protective ozone in the stratosphere. Very good. So we've been talking about concentrations. What does ppb as in Boyd stand for? Parts per billion, exactly. So in the stratosphere, you're looking kind of at a max. You can kind of think of this guy right here as being 12,000 parts per billion, okay? And it decreases. So what do you think? How would you compare this little blip to this amount? It's pretty small. This is our bad ozone. Okay, this is the man-made. Okay, but the good ozone is a lot more. That's kind of surprised me as I was getting ready for this lecture, because I'm like, because my thing's always been smart aleck, and actually I think there's a cartoon, I'm going to have to find it in your textbook, that says, why don't you just pipe this stuff up there? If this is depleting or if this has issues, go ahead and take our bad ozone. I don't know, maybe Elon Musk can do it. Okay. So words I have here, it looks like down here, yeah, this little blip right here, instead of 12,000, it's 20 to 100 parts per billion in the troposphere. So here we have O2, because remember oxygen is one of those things, one of those 7 elements, likes to be paired up. And then here we have O3. And we talked about this on Friday, that as it turns out, actually the bond between these 2 oxygen atoms is stronger than the bonds connecting these 3 oxygen atoms. So this is strong. Okay, so use the figure on the previous slide to estimate the approximate elevation and maximum ozone concentration. So what do you think? Where's the maximum ozone concentration? Yep, 22 kilometers. Okay. From the previous slide, what's the maximum number of ozone molecules per billion of molecules at, that should say of atoms of all types found in the stratosphere? What do you think? Let's not make it too complicated. This is what I was after. Okay? I was just after that 12,000. 12,000 parts per billion. That's it. That's it. But I think the point for the B question, the C question is, remember how that works, that in 1 billion molecules up there, you're going to have 12,000 of them out of 1 billion. 12,000 of them are going to be ozone. That's the way that works. Okay, so I went ahead and went back for you and didn't make you do it. But in chapter 2, remember where I put the standards, like if you're exposed to ozone, what limits are you talking about? I think the other ones were, was it carbon monoxide and maybe sulfur, or NOx's maybe? There was 4, and particulates. There were 4 things that the EPA says, thou shalt not be exposed with this limit. And if you go back, you're going to see an 8-hour average for ozone here in the troposphere is 0.070 parts per million. And I guess my first thing to ask question to you is, how would we convert that? I know you guys love conversions. How many parts per billion is that? I'm liking 70. You see how that, because they're a factor of 1,000 between the million and billion. Yep. Cool. And so then my point is if you guys say we have 20,000 parts per billion in the ozone layer. And I'm not asking you to do any math here, but how do those two compare? Yeah, I don't necessarily want any math, but just in general, how would you say? Yeah. I found this interesting too, as you can imagine. You can tell. So all I'm saying is if we were to go up to the stratosphere, we'd OD on ozone, wouldn't we? Does that seem right?
So it wouldn't just be like a lack of oxygen. Would you OD on ozone right away since that one's for 8 hours?
Yeah, will it happen right away? Not necessarily. And then the other thing is we're going to talk about, you guys told me how the air thins as you go up. So 70 parts per billion, or even 12,000 parts per billion. If you have fewer gas particles, you know how that works? It's like, well, then you have fewer of them per area. I don't know if that makes sense. It's just diluted up there. More space between particles. I just thought that was interesting. So I think this kind of drives me nuts. As somebody who, we dabbled in parts per million, we dabbled in parts per billion, we kind of talked about milligrams per liter, that sort of thing. But for ozone, they came up with a new unit, and I read in your textbook just a little bit about how Mr. Dobson came up with this, blah, blah, blah. But anyway, the good ozone in the stratosphere, the way they measure it basically is at the ground, they have a detector that says, well, how much ultraviolet radiation is getting in? And then the less that gets in, the stronger the ozone layer. If we get a lot of ultraviolet radiation coming in, that means our ozone layer is wimpy. Okay, so that's how they do it. And then the other thing, I just think this is bizarre. So it looks like I have 3 millimeters there. So what they do, and this is did you guys know that gases are compressible? We could take gas, you can get compressed air. You buy compressed air so gases are compressible. So what they do basically, kind of thinking along those lines, is they take a column of air like you see there, and they shrink that column of air down, just picking on the ozone particles of gas, the ozone molecules of gas. Then they go ahead and shrink it down. You see 3 millimeters? I didn't bring in we got a yardstick. 3 millimeters. This is ozone, column, stratospheric ozone. So there's 3, okay? So basically squeeze it down there, okay? And if that is let's see. Now, gases have different pressures at different temperatures, too. You guys probably, what do you think if you heat up a gas? Does its pressure increase or decrease? Or if you heat up a gas, pressure increases. So here we're going at a pretty chilly temperature, 0 degrees Celsius. Not absolute 0, but 0 degrees Celsius. So you cool that air to 0 degrees Celsius, or warm it to 0 degrees Celsius if you're in a cold place. And you push it until you get a pressure of 1 atmosphere. Now you're like, well, I don't know what pressure 1 atmosphere is. Well, as you're walking around this room right now, that's a pressure of 1 atmosphere. Nitrogen, oxygen, 1 atmosphere. So basically they pick out they have to do this theoretically. They pick out the ozone particles at 0 degrees Celsius, and they make a little slab down here on Earth that is 3 millimeters thick, and they call that 300. You're like, could you get any crazier? I just think that's bizarre. Is it just me? I don't know. Maybe I need to read about it some more. But they would call that 300 DUs. Okay, now, if you had more O3 molecules in your ozone layer, you would get a thicker slab. So 500 DUs is 5 millimeters. I just think that's bizarre, okay? And again, that has to do with the ozone above you. Now, we'll be talking more about this ozone hole and that. But one of the things we've already talked about is that UV index. The UV index would take into account the DU scale at your location. So, anyway. Just craziness. Craziness. Oh, okay. So tomorrow's lab, you guys are going to be dabbling with looking at compounds or looking at molecules, and you're going to be drawing them. So I have taken the liberty of, since I do this in my other classes, kind of hybridizing what our chemistry and context textbook, how they say to draw Lewis structures, and how I've been successful at drawing Lewis structures. And it follows these steps. So did we, I think we did, where's my I have a periodic table. You did make a periodic table, Sandy. I know we talked about valence electrons. For the group A elements, how do you know how many valence electrons? For instance, how many valence electrons for a carbon atom? Here's our periodic table. No? Oh, right. Yes, it is 4. Thank you. Sorry. Yes, it's 4. And how'd you get 4?
Has 4.
Because it was
Group 4. It's group 4. Oh, so he's, awesome. He's looking at those little numbers, the tiny little numbers. In the upper right-hand corner for carbon says 2 and 4, and actually that's how the electrons are configured. And so the 4 is the valence electrons, perfect. And then Taylor did it just because of, he did it just because of the group number. Yep. Yes. So in order for this to work, for me to show you this morning, and then for you guys to do your lab tomorrow, one of the things we have to all agree on is that if you look at the group number, you know how many valence electrons it has if it's a main group element. So what group is oxygen? I know it says 16, but what else did I say to put above it? 6A, so it has 6 valence electrons. Perfect. How about potassium?
Okay,
1A, so it has 1 valence electron. Perfect. Exactly. So the first step in drawing your Lewis structure is to come up with what I call a pot of valence electrons. Okay, a pot of valence electrons. Add them all up. Now, the second step, and I'm not sure in chemistry and context when we'll get to it, I think we'll get to it with regard to compounds, but there's this thing, I'll just throw, it sounds like a bad word, but electronegativity. And it just has to do with how electrons want to grab on, how atoms want to grab onto electrons. But what you need to know to draw your structure is this. And it has to do with placing atoms in the center. So the three words I have are left, lowest, and center. Left, lowest, and center. Now, when you're going to draw your structures, they're going to be relatively simple structures. So you will have something in the center and other things kind of extending out from that atom, one center atom. So the one that's going to be in the center is going to be, I get my lefts and rights mixed up. It's going to be the left. If you have an option between putting different atoms in the center, you're going to pick the one that is farthest here and farthest down. Okay, the lowest electronegative. All right. The other thing I have up here, and it will be important, is hydrogen never wants to be in the middle. It always wants to be on the outside. These are just general rules, and we'll do an example here. And then we'll hit this tomorrow. So you are going to then connect your atoms with one dash. That one dash is going to be a bond, a chemical bond, your one dash. And bonds actually represent, now how many are in a pair? Like P-A-I-R, how many? 2, exactly. So you'll have, anytime you see a dash connecting atoms on a structure, that's 2 electrons. Pair of electrons. Perfect. So these are just kind of steps, and these are actually kind of the order that we do them in. Now, distribute, that's a kind of a big word, but distribute just means to throw around, right? So after we have our dashes drawn between our atoms, we are going to look to see how many we have left over, basically. We're going to say, remember you had that pot of valence electrons, and then from that we're going to subtract anything we used up in dashes. And our goal, ultimately, with drawing our structures, are going to be to get atoms to have access. Now, sometimes these electrons are going to be shared, but atoms need to have access to 8 electrons on your final Lewis structure. And there are 2 exceptions. What are the 2 exceptions? Hydrogen only once. A deuce, 2. A deuce. And the other one is, what's B stand for? Boron. Oh, goodness. Oh, that's terrible. I must have been hurried. That 6, that 8 should be a 6. Goodness gracious. Only 8 electrons? That should be 6. Sorry, guys. Okay. Yeah, B is boron. The element boron, if that's in your structure, it only wants to have 6 electrons.
Why is that? It's just what it does.
I'm trying to think. It's just what it does. I'll have to double check. Good question. So I call it swinging. So here's the deal. Oh yeah, I didn't say that. Oh yeah. For the step up here, in order to get things 8 electrons, you know, if you've already added your dashes, you don't need necessarily any more dashes. So what we're going to do, and I call them dot dots, like if this is my, let's pick on oxygen. Okay, these dot dots are a pair of electrons that are by themselves. So we call these lone pair, like the Lone Ranger, lone pair electrons.
There's the ones that they already have 8, so you don't need those 2.
I don't know if we can answer that in context, so hold that thought. Probably. So here's the deal. When we kind of start to wind down, drawing our Lewis structure, sometimes you're going to see, especially the middle atom doesn't have 8 electrons yet. So here's what we do. We basically, and this isn't in context of anything, but basically we can swing lone pair electrons in to make a double bond. If one dash is 2 electrons, 2 dashes, we call a double bond, is 4 electrons. 3 dashes, 6 electrons. I felt like Carl Sagan when I said that. Okay? It's easier to show you. So to check to make sure your Lewis structure is solid, okay, you're going to double check that each atom has a complete set of 8 electrons that it either has sole custody or joint custody on. And the other thing is you're going to make sure that the pot of electrons that you had in your first step shows up on your final Lewis structure. Now boron only wants 6 and hydrogen only wants 2 in your final Lewis structure. So instead of going on to the next one I was going to do, let's pick on, let's do a few. Let's pick on water. And this might have been what you were thinking, Taylor. So this is how I do it. So if H2O, I think I'll go clear over here. So I can have room to go across. I think this is how I'm going to have you do it in your notebooks tomorrow. So H2O, that is the molecule. Okay. I'm going to say valence electrons. So what I would do is I will take 2, because I have 2 hydrogens. How many valence electrons for each hydrogen? 1 valence electron. And I have 1 oxygen. How many valence electrons? Find it on the periodic table. I'm going with 6. And don't feel shy if you have to get out a calculator, because sometimes I do. But I'm like an 8 electrons. Perfect. And then your next one is going to be, I'll just put this, I'll put this as simple structure. And what I mean by that is it's just going to draw in that initial chemical bond. So our options are to put hydrogen, have hydrogen, hydrogen, oxygen, or hydrogen, oxygen, hydrogen. Which of those two make more sense?
Hydrogen, oxygen, hydrogen.
Hydrogen, oxygen, hydrogen. And this goes with, I said hydrogen never wants to be in the middle. So I would think of it this way. Oxygen in the middle, and there's one chemical bond, and there's another chemical bond. Simple structure. Now, with this step, the simple structure step, what I usually do is say, well, how many electrons do I have left? Maybe I'll make it this way. I'll just make another column. Remaining electrons. And what I mean by that is my pot, I'll put this pot of valence electrons. My pot was 8. Okay, how many electrons have I used here? 4. I used 2 electrons there and 2 electrons there. So 8 minus 4 remaining electrons.
You 2 dots on the top and 2 dots on the bottom.
So, yep. So my next one is to distribute remaining electrons. I'll just put DIST, distribute remaining electrons. Okay. So I redraw my simple structure, oxygen, hydrogen, hydrogen, and I take these 4 electrons and I'm going to do, I call them dot dots. I'm going to keep them in pairs. Now, right off the bat, is hydrogen happy already?
Yeah.
Yes, hydrogen's already happy because it's got 2 electrons and 2 electrons. But how many electrons around your oxygen atom now? There's only 4. So actually, I'm going to take these remaining electrons, I'm going to put them in pairs, and go just like that, just like the other side. So, that's it.
That's what I'm used to doing, just like drawing the picture.
What's that?
Just like drawing the picture, like how to connect, put them together.
So let's do another one. Yeah. So actually, this last one, I'll call it swing electrons. So I'll put swing lone pair electrons, question mark. Now, this step might be not applicable. And the reason it's not couldn't be not applicable is if everything already has either 8, like oxygen has 8 now, right? 2, 4, 6, 8, or 2 for hydrogen, or 6 for boron. We don't do boron very much, but okay. So actually, we don't need to swing any here. So I'm going to put Na for that one. If that's the case, then this one is your final Lewis structure.
How do you never put oxygen in the middle?
Because hydrogen never wants to be in the middle. And if otherwise, we would find ourselves going to the periodic table and seeing which one's lower. Okay.
The biggest one goes in the middle, doesn't it?
The one that's in the middle goes, just what I said. The one that's further, if it's in the same period, it's further over here or further down. What's lowest electronegative?
Is this the same as like when you draw the wings and then put the dots on them?
I think
Yeah,
so.
that's what I keep thinking. Like that's how I know how to do this.
Okay.
It's like where you just draw the picture and then put it in.
Okay. Probably, yeah. Because so that's what we'll double check tomorrow, but probably. Yeah, I think so. The wings.
Yeah.
Okay. So let's do another one. I'm trying to think. Actually, you guys have one coming up.
HBR or BR2.
Okay, so those are the cones coming up. So let's go with O2. You're like, how hard can O2 be? Well, let's do the steps. So, and then like if these aren't the steps you're used to using in your notebook, then tomorrow at least come up with something to show how you got your structure. So O2. So we have 2 oxygen atoms. How many valence electrons? 6. I'm liking it. Group 6A. So 12 electrons. Cool. So our simple structure, like there's not really one in the middle, so I'm just going to do this. Right? Simple structure.
Are we doing like a triple bond?
So got to do it systematically. Because no. So the remaining electrons, how do we calculate this? So what's our pot?
Minus 2.
Yep, 12 minus 2. So we have 10 electrons remaining. You guys, we have to do it systematically. But yes, it's not triple, it's a double bond. So systematically, so I redraw my simple structure. And I go ahead and let's see, 10, it gives me 5 pairs, right? Does that seem right? Well, none of them's happy. Neither one of these guys are happy, so I'm gonna go ahead and start doing it this way. That's 4, 5. Wait.
No, you're missing. Didn't you move the other one to the other side?
Oh, I'm missing one. 1, 2, 3, 4. Yeah, there. That's better. So this is 12 electrons. 2, 4, 6, 8, 10, 12. So, yes, we have to do some swinging here. So I could, if I swang this one here, then that would give this guy, what, 10, right? And this guy would have 6. It's this guy that has the problem, the guy on my right. So actually what you're going to see is if I swing, and I can choose any of these sets. I can choose the south, the west, the north, but I'm choosing the south one. What the swinging does is to create a second bond. Yeah, making a double bond. And then I redraw what I had and what I have left over. All right. Now a few checks on our final Lewis structure. So let's see, if I were to draw kind of a Venn diagram sort of around this oxygen at 2, 4, 6, 8, that works. This guy, I have 2, 4, 6, 8. Yeah, so they both have a complete set of 8 electrons there. Okay. Now, it's funny, and I can kind of see why we do it, but lone pair electrons really are players in how a molecule behaves. So lone pair electrons are like, they're invisible. How could they? Well, they really do. They really do add function to the molecule. Okay, so I know this looks messy, but yeah, it's oxygen, double bond, oxygen, lone pair, or lone pair, like that. Okay. Let's see what we got. Okay, so we haven't been dealing with O2 as much as O3, which is ozone. So up here, we're gonna kind of just do the same thing we did and see what we end up with. So you guys, there's 3 oxygen atoms in O3, and each of them brings 6 electrons. So we have a pot of 18 valence electrons. So our next step was to go ahead and draw the simple structure. You're like, well, you know, who do you put in the middle? Well, they're all oxygen atoms. So I'm going to put that one in the middle. So with regard to how many remaining electrons do I have? 14. I have 14, yep. I have 18 minus 2, 4. So I have 14 electrons I can distribute around. And this might be kind of a little bit with the wing thing, but the wings were always 2 electrons, right? I don't know. I'm trying to decide how you guys learn your Lewis structure. But were there always 2 electrons with each like electron domain wing?
Yeah, like the first ring was only allowed to have 2. And the second one 4, and then it doubles as it.
Oh.
2, 4, 8, 18, and then it goes.
Yeah, I think
and
that's.
then it goes back down.
I think that's electron configurations like that. The 1s2, 2s2, 2p6, 3s2, 3p6. Yeah, that sounds like. Oh, well, we'll just see. Okay, so 14 electrons. What I was going to say is pairs, so 7. So we have 7 pairs. Now, the way I learned it is we want to make our outside atoms happy first. They call them terminal atoms. So if I call these from left to right A, B, and C, oxygen atom A, B, and C, can you see where oxygen atom A and oxygen atom C are my terminal atoms? Okay, so I'm going to make them happy first. So let's see, if I have 7 pairs, so wow, 1, 2, 3, 4, 5, 6, and only then do I turn my attention to atom B. Okay, you see how that works? So again, I call this a preliminary Lewis structure. We're not done yet because even though atom A and atom C are great with octets for a set of 8 electrons, atom B is not happy. How many electrons does atom B have?
2, 4, 6.
I'm thinking 6. Yeah, 2, 4, 6. It has 6. So we have to swing. Now the word is resonance structures. So actually this gets to something in structures where we could either swing, and they're great, they're both valid. A, we could take a pair of electrons and make it a double bond with B, or atom C, we could take a pair of electrons, swing it in and make it a double bond with B. So I'll do both. What the heck? So this one, if I swung in this pair of electrons, that would look like what? Oxygen, double bond, oxygen, single bond, oxygen. And on this first one, I shall have 2 lone pair electrons. On the middle one, I have 1 lone pair electron. And on the far one, I have 3 lone pair electrons. Alternatively, if I swing this way, I end up with my other structure, which is oxygen, single bond oxygen, double bond oxygen. On the first one, I still have 3 pairs of lone pair electrons. The middle oxygen, 1 pair of lone pair electrons. And since I swung from atom C, I only have 2 lone pair electrons there. Actually, these are both great. They're called resonance structures. And some resonance structures make more sense than others. So actually, what I've seen it is like an arrow, a double arrow, to kind of show that they kind of go back and forth. They're both fine. So there is ozone. Ozone. So you guys got time. See what y'all do with these. I know I need to keep an eye because that clock's a little off. Ooh. Goodness, they're loud today. So some of you, what is the word missing on the last slide? The letter R. R. Resonance structures. So we'll start with this on Wednesday. Meantime, I'll see you for that tomorrow.
I sent you the link to that video I watched.
Thank you. Cool.